In this video, we're going to have a look at magnetic resonance imaging, or MRI. You may have had this when you've been at hospital. The machine looks like this. If you are absolutely loaded, it might be a good Christmas present, but they are very expensive and require a lot of electricity. Patient goes in here, looks ominous, but it's actually it's actually incredibly safe. We'll talk about that in a minute. And inside here, we create a very strong magnetic field. We then use the ideas of resonance to create an image, which is useful to diagnose things. I mean, take this example here. You get incredibly good detailed images of the body. And you can see they've spotted a tumour here. And this is amazing when you think about it, because otherwise you'd have to go dicing them up or using other techniques like x-rays, which aren't as good, and they are also dangerous to cells. You can also have a bit of fun if you do get this for Christmas and look at fruit and vegetables underneath. This is a corn there. And if you just search Google, you'll see some amazing ones of broccoli. And one of the key advantages of MRI is you can create layered images, so you can really diagnose down to the three-dimensional point of where the problem is or where something is. So it creates amazing images. And if you watch the GIFs or the GIFs of fruit and veg, you'll see that there. You might also see this sometimes called NMRI, with the N standing for nuclear. Now, you can probably guess why they've stopped using that term, nuclear, because it's not that appetizing when you're about to go for a scan, and they've binned that off, even though this has nothing to do with nuclear fission or fusion or radioactivity. The nuclear refers to the nuclear of atoms. It's got nothing to do with radioactivity. Okay, so don't panic. It's actually incredibly safe. It just uses radio waves, which are going through your head right now from your local radio station, and strong magnetic fields, which, as we know, are not of any harm. So, how does this work? So this relies on the idea that some nuclei have a property called spin. This is a bit like some particles have a property called charge. We don't know why the universe has these properties, but some nuclei do have this property called spin, and the proton is one of them. Now, the key idea here is that any of these things that do have this property called spin actually behave like a small or tiny magnet when they're in a magnetic field. So they actually have a kind of north and south pole caused by this spin, and this is really useful. Let's take hydrogen. Hydrogen consists of a proton and an electron. And as you can guess from the name, nuclear magnetic resonance imaging, which we don't use anymore, but we're interested in the nucleus. So we're just going to look at the nucleus of a hydrogen atom, which is actually just a proton. Now, protons do have this property called spin. So they actually behave like small magnets. So rather than write proton, I'm now going to represent them with an arrow like this, with that being the north and that being the south pole. So if we now have lots of these protons together, which you have in your body, everything with water has hydrogen in, and that is a proton. If we just leave them, we look at a random sample, they're all going to be pointing in kind of random directions like this. But if we now get one huge bad boy magnet, and make that say north and this south, well, what are these going to do? Well, as you can imagine, the majority of them are going to orientate themselves with this field. So north's going to be attracted to south. So most of them are going to be like this. There might be a few bad boys, a few rogues pointing the other way, but the majority are going to be like that. But they don't actually line up exactly straight like this, and this is the thing we exploit in MRI. Now, how does it do this? Well, I've done a sketch here of a proton, which is represented by this sphere, and you can see it's rotating or spinning round its axes. Its axis of spin, a bit like the axis of spin of the Earth, is here, and it's tilted. Now, what happens is this axis of spin actually precesses around the magnetic field. We call this precession, and the path is shown by this dotted line. So just a reminder, we've got a proton which is spinning, as shown here. And when there's a magnetic field, it lines up pretty much with that magnetic field, but not quite. And it actually precesses all this axis of spin, moves around that magnetic field. So a moment later, this proton will be spinning over here like that. So it's moved around. Now, this frequency of precession, so how quickly it goes around like that, is called the Larmor frequency. Now this depends on a number of things, but the main thing it depends on is the strength of the magnetic field. So we'll call that frequency, it's kind of like an angular frequency, is related to the strength of the magnetic field. If we make the magnetic field stronger, this is going to go around here quicker. Now, in a typical MRI, B is approximately 1.5 teslas. It doesn't sound much, but that is a lot. And if we put that into the equation, which you don't need to know, we find that the Larmor frequency, which again I'm just giving it that symbol omega L, let's call it, is approximately equal to 60 to 70 megahertz. What's special about that? Well, that frequency happens to be in the radio frequency region. So this is a radio frequency. So this precession, the rate at which it goes around in this circle, the number of times it does that per second, is very close to the frequency of radio waves. Useful, I think. Maybe you've seen where this is going, because the name frequency is in MRI. So if we know that these protons precess round at 60 to 70 megahertz, if we match that frequency by using radio waves, because we know they have a similar frequency, it's going to cause this to resonate. And that is very useful. So what can this energy do? Well, as we said earlier, we had two parallel magnets, and we had all of our protons, pretty much all of them, aligned this way. Why? Because that was the lower energy orientation. This was a south pole, this was north, so this is the natural orientation. But if we now send in these radio waves, they're going to cause these to resonate, gain energy, and that means they can actually flip the other way around. So if we give them just enough energy, we can get them orientating in a high energy orientation. This is the north pole, this is the south pole, so they're now repelling. And the clever bit is we now switch off the radio waves with them all excited to this higher energy level. So there go the radio waves. And what are they going to do? Well, I don't know about you, but if I'm a magnet, I'm not going to want to stay like this. So after some time, which we call the relaxation time, and this depends on the material that that atom finds itself in. So if it's a cancerous tissue, the relaxation time will be slightly different to if it's a watery or a fatty tissue. In fact, if it's a watery tissue, the relaxation time can be up to several seconds, whereas a fatty tissue is a much shorter time. Cancer, whereas cells tend to be somewhere in the middle. So as they relax back down now, remember there is no radio waves keeping them exciting that orientation. They're going to flip back down and they're going to emit that excessive energy as radio waves again. So they've absorbed them originally, been excited in the opposite direction, and now they relax back, just taking a chill, and they emit that radio wave. And that's it. The doctor, or well, a computer, detects this, processes it, and produces the MRI image that the doctor sees. Now, there's a bit more you need to know about this. And these main features tend to be the things they ask in the exam. The first part is the large magnet, which creates the uniform or constant magnetic field we talked about earlier. It's very large. This might not seem large, but 1.5 to 2 teslas is huge. And that's why we need a superconductor. And this is why they're really expensive to run. And also, they require liquid nitrogen to keep them cool so that a lot of current can flow. Remember, current creates a magnetic field, and that's what creates this uniform field here. Why do we do this? Remember, it initially aligns the protons up with the magnetic field because of that property called spin. And remember that we need this large value of B, the magnetic field strength, because we need the Larmor frequency to lie in the radio region of the electromagnetic spectrum. The second important part of an MRI machine are the gradient cores. And these are further cores that create a magnetic field. They're not as strong as the one just mentioned above, the large magnet. And they're non-uniform, so they need to vary the magnetic field. Now these are along the length of the human in the machine. So if here's our human, they're all along like this. And the reason being is they can adjust the magnetic field at any point along the length, the width, the depth, such that it matches the exact magnetic field that they're interested in to create that exact Larmor frequency that they're interested in. And that way they can work out which bit they're looking at. Since once the radio waves have stopped from this side, remember that these are going to relax, the nuclei are going to relax, emitting radio waves back out. And we're not going to be sure where they come from. So the way they know that is using a computer obviously, they set the magnetic field to be at just one point, the exact field strength that we need to produce those waves of the exact frequency we know we're looking for, so we can know exactly where it's come from. What do you need to know for the exam? Well, the idea is that these gradient coils produce an ununiform magnetic field. And remember that the Larmor frequency depends on the strength of the magnetic field. So if we vary the magnetic field across the body at different depths, different points, we know that the nuclei can therefore be located. Why? Well, remember that the frequency depends on the magnetic field strength. So if we take our human, the magnetic field strength here is, say, 1.55 Tesla, and here is 1.65 Tesla. They're both going to emit different frequencies of radio. So we can then know exactly where that's come from by measuring this frequency and knowing the strength at these points. This is of course all fed into a computer which does the calculations, and that's another key component of an MRI scanner. And the other two that are worth mentioning, we have some radio producing coils and also radio detecting coils as well. And the clue is pretty much on the tin there. Now let's look at the advantages which they can ask. Okay, the first one, obviously, a big advantage is the patient feels nothing during the scan. There's also no moving parts, which makes it easier to maintain. The big advantage over CT scans or X-rays is that there is no ionizing radiation, and therefore no harm caused to the patient or the person doing the scan. You'll notice that actually doing an MRI scan, the doctor and nurse will be in the room at the same time. One thing you can't have, though, is any magnets or any metallic stuff on you, because obviously that's strong magnetic field. It also gives you a better contrast than some other scans. And it can also produce that three-dimensional layered sort of walkthrough of the body, which makes it easier to pinpoint any issues. Finally, we're just going to have a look at some exam questions, but obviously do take a break before we look at those for the next couple of minutes. First question is there. Feel free to pause it and read it over in detail and have a go at it. The key part of this question is asking you to state and then explain. So state what it does and then explain the purpose of the large constant magnetic field and the non-uniform magnetic field. The answers are basically what we had written down here. The parts in blue explain the point of the large magnetic field. Bear in mind that it aligns the protons initially, and this causes the Larmor frequency to be in the radio region because we've tuned that magnetic field strength there to match the radio frequency region. What do we use the non-uniform magnetic fields? Well, they're your gradient coils, and the answer is there. The Larmor frequency depends on the magnetic field strength, as we know, and therefore if we set B at any point, it allows those nuclei to be located because that B is related to a Larmor frequency, and if we know that frequency, we know where that emission of that radio wave has come from. So that's your answers to those two. The next question, and this is somewhat ironic because it asks you to explain briefly and then gives you all of this and 8 marks. So this really is a good cash cow of a question. Have a go at answering that, and I'll put the answers up in a moment. And here are your answers. You need any of these 8 points, and each line is a point. First one, the idea that you need a strong, large, uniform magnetic field. That was kind of addressed in the question above. The nuclei precess or rotate around the field direction. Remember, because they have that property of spin, they act like little magnets and they precess around the direction of this large uniform field. We then put in some nice radio frequency pulses at the exact frequency that caused them to resonate, the Larmor frequency, which depends on the magnetic field strength. And as we know, it's in the radio region. This causes resonance, or them to absorb energy, which excites them. When they relax or de-excite, they go down to a lower energy level and they emit radio frequency waves, pulses. These pulses or waves are detected and processed by a computer. Now that's all well and good, but how do you know where they're located? Well, we need to use a non-uniform field, which is superimposed on this uniform field. It means it's there at the same time. And that changes the strength very slightly at different points in that body. This allows the position to be detected. And since we know the position of where that nuclei was, we know the location of where that came from, we can build up a three-dimensional image. So that kind of brings in parts from the answer to question 1 up there. They're the two most common questions. And just before we finish, we'll have a look at this nice image here, which sums up MRI in one nice image. So remember, we're looking at protons in hydrogen nuclei in your body, and they have this property called spin. They spin around an axis, which is shown in purple here. So they're spinning around like this. They're having fun by themselves, but when a magnetic field comes along, things start to get interesting for them. You can see the magnetic field's on here, and you see they've all aligned themselves. But actually, remember that they slightly precess in their spin when that magnetic field is on. The magnetic field, say, is in this direction. So they precess around like that. Again, all well and good, and this precession has a frequency called the Larmor frequency, which is related to B. And it happens to be in the radio region, so we put in a pulse of radio waves there. This causes some of them to be excited and move their precession into another orientation. And this is a higher energy orientation. As soon as it's switched off, they don't drop down immediately. There's something called a relaxation time, which depends on their location, which gives information about that region. And when they do relax, they re-emit their radio wave, which can be detected. And because we've slightly changed the magnetic field around the body, in an adjacent part, say down here, those will not be at the Larmor frequency. They wouldn't be processing at the Larmor frequency, so they would not get excited. So we know exactly where that radio wave has come from. And therefore, we can make up a 3D map. Thanks for watching the video. I suggest you read the notes and any other resources to help you understand this. Make sure you practice questions as well. Have a good day. Thank you.